Hello, everyone. My name is Tyler Ladge, and today I'll be going over some physics concepts that I learned in college. The concepts that we will be going over today are number one, scalar and vector quantities, number two, work, and number three, energy. Scalar and vector quantities. What is a scalar quantity? Scalar quantities are described solely by their magnitude, size, or quantity, and do not have a direction associated with them. Some examples of scalar quantities are temperature, energy, speed, angle, distance, area, volume, frequency, time, and etc. An example of a scalar quantity is distance. Distance traveled by a car is a scalar quantity because it only tells you how much ground an object has covered without indicating direction. For instance, if a car travels 50 kilometers, it doesn't matter in what direction it traveled, only that it covered a distance of 50 kilometers. Here we have an example question of a scalar quantity for distance. The question: a car travels at a constant speed of 60 miles per hour. How far will it travel in 2.5 hours? For this question, we will use the distance formula because speed and time is given to us. To calculate that, you'll plug in your components into the equation: 60 miles per hour times 2.5 hours, which will give you a total distance of 150 miles per hour. 150 miles. So the car will travel 150 miles in 2.5 hours at a constant speed of 60 miles per hour. What is a vector quantity? Vector quantities are described by both magnitude and direction. They represent physical quantities that have both size and direction. Some examples of vector quantities are position vectors, displacement, velocity, acceleration, and etc. An example we have here is for velocity. Velocity is a vector quantity because it describes both how fast something is moving, its speed, and what direction it is moving. For example, if a car is moving at 60 kilometers per hour magnitude towards the north direction, its velocity is represented as 60 kilometers an hour north. Here we have an example question for velocity. A car starts from rest and accelerates uniformly to a velocity of 20 meters per second in 5 seconds. What is the average velocity of the car during this time interval? For this question, we will use the average velocity formula, which is initial velocity plus final velocity, which gives us our average velocity. Now we will just plug in what is given to us: our final velocity, which is 20 meters per second, and our initial velocity, which is 0 meters per second. The reason why it's zero is because the car starts from rest. When you plug those into the formula, you'll get a total of 10 meters per second. So the average velocity of the car during the 5-second interval is 10 meters per second. Our second concept, work. So what exactly is work? In physics, work refers to the energy exchange with an object when force is exerted over a certain distance. Simplifying it, when a constant force acts in the same direction as the object's motion, work is calculated by multiplying the magnitude of the force by the distance traveled. Mathematically, work is given by F times D times the cosine theta. W is the work done, F is the force applied, D is the displacement of the object, and theta is the angle between the force vector and the displacement vector. Work is also measured in Newton meters, which is equal to joules. An example we have is lifting a box. When you lift the box off the ground, you apply a force upwards, and the box moves vertically. The work done is the force you exert multiplied by the distance the box moves in the upward direction. Here we have an example question of work. A person applies a force of 50 newtons to push a box along a horizontal surface. The force is applied at an angle of 25 degrees above the horizontal. If the box moves a distance of 8 meters along the surface, calculate the work done by the person. So here you see we have the person pushing the box at an angle of 25 degrees with a force of 50 newtons and the distance 8 meters. First, we need to find our force horizontal. So with that, we will use the formula F times cosine theta. When you use that formula, your total answer should come out to be 45.315 newtons. With that, you can now use the actual work formula, which, like we said before, is F times D times cosine theta. You plug everything in, It should be 45.315 newtons times 8 meters times cosine 25. Once you put that in, your answer should be 327.6 newton meters or 327.6 joules. Lastly, concept number 3, energy. What is energy? Energy is the capacity to do work. There are various forms of energy, including kinetic energy, which is the energy of motion, and potential energy, which is the energy due to position or state. Kinetic energy. Kinetic energy is the energy an object possesses due to its motion. It is calculated using the formula Ke equals 1 half times m times v squared. M is the mass of the object, and v is the velocity of the object. Potential energy. Potential energy is the energy an object possesses due to its position or configuration relative to other objects. It's calculated using the formula Pe equals m times g times h. M is the mass of the object, g is acceleration due to gravity, and h is the height of the object when it was dropped. Some examples we have: a moving car has kinetic energy because of its motion. A raised weight has gravitational potential energy due to its position above the ground. And we have a stretched spring has elastic potential energy because of its deformation. Here we have an example question of energy. A 0.5 kg ball is dropped from the height of 10 meters. Calculate the potential energy of the ball when it's dropped, the kinetic energy of the ball just before it hits the ground, and the total mechanical energy of the ball at the instant just before it hits the ground, assuming no energy was lost. So A, we must calculate our PE. So we will use that formula like stated before. PE equals m times g times h. What is given to us is the mass of the ball, which is 0.5 kg, our acceleration due to gravity, which is 9.8 meters per second squared, and the height, which is 10 meters, the height from which the ball is dropped. If you plug all those components into the PE formula, you should get a number of 49 joules. For part B, the kinetic energy of the ball just before it hits the ground is given by Ke equals 1 half times m times velocity squared. V is the velocity of the ball just before it hits the ground. Since the ball is dropped from rest, its initial velocity is 0 meters per second. Using the principle of conservation of energy, all the potential energy is converted into kinetic energy at the bottom of the fall. Therefore, PE equals Ke. So therefore, Ke also equals 49 joules. Lastly, the total mechanical energy of the ball at the instant just before it hits the ground is the sum of its potential energy and kinetic energy. So our total energy will be PE plus Ke. So we will do 49 joules plus 49 joules, which equals 98 joules. So the total mechanical energy of the ball at the instant just before it hits the ground is 98 joules.